We're now going to do our second proof of the generating function for the signless Stirling numbers of the first kind. And this proof is going to be purely combinatorial. In order to give a combinatorial proof, we need to have combinatorial interpretations of both. So this has a combinatorial interpretation right here, okay? So we need to figure out, just using this expansion over here, what's a combinatorial interpretation for the coefficient of x to the k? And then we're going to have to show that that's equal to the Stirling number. Okay, so let's build that up. We're going to use the same notation as before. We're going to let fn of x be the rising factorial, x plus 1, all the way up to x plus n minus 1. Okay, and then we're going to think about expanding this out. And what is the coefficient of x to the k in fn of x? Well, how do we get a term with x to the k? I'm going to think about, for each number here, I can either pick the x for each term. I can either pick the x, so we'll do that k times, choose x, k times. And the other thing I could do is choose the number. So whenever I don't choose the x, I'm going to choose the number, and that'll happen n minus k times because they're a total of n terms. Okay? So what is that telling us? That's telling us that the coefficient here is going to be equal to the sum of choosing the numbers. Well, which numbers do I choose? So I could choose, let's say, a1, a2, might as well take them in order, up to an minus k. How big are those numbers? Well, the biggest one is n minus 1. Okay, and then I'm multiplying them together when I choose them. So a1 times a2 times an minus k. Okay, so that's what the coefficient is. So I have to choose xk times, and this is what I choose here. And of course, these numbers are at least 1. And I have to unpack this again because this still isn't a combinatorial interpretation. It's still a formula, okay? So what I want to think about, what am I summing over? So this is going to be an n minus k subset of the numbers 1 up to n minus 1. That's a combinatorial thing. That's a binomial coefficient with a combinatorial interpretation. That's fantastic. I know what those are. What is this up here? This is when we have a product, we're choosing, you can think of choosing a number 1 up to a1, choose a number 1 up to a2, choose a number all the way 1 up to ak. So this is going to be choosing 1 from each of a1, a2, these sets, an minus k. That's how we get that number. That's the combinatorial interpretation of a product. So now with all that in mind, I'm going to let omega sub nk equal the set of, I need it to be a set of objects. It's going to be a set of pairs SF, okay, such that S is going to be the subset of n minus 1 of size n minus k. And what is F? Well, I can think of F as choosing a number, which I'm going to write like this. So F of F is going to be a map from S. What's the biggest these numbers could be in theory? Well, they're n minus 1. So it's a map from here. But for each one, F of I want it to be less than or equal to I. Okay, so maybe now is a good time to give an example and start building an example up. An example of an object that's in this S, in this set omega. So let's let n be something nice and big, like 9, and we'll let k be reasonably big as well, which is 4. Okay, and just to keep track of things, even though it's really obvious what this is, n minus k, a derived number, this is 5. Okay, so I'm going to choose, I want to choose S of size 5 and a map F from S to the numbers 1 up to 5 such that F of I is at most I. Oh, sorry, not 5, 8. Okay, n minus 1 might be another number to write down so I don't screw it up again. So let's just make a choice. We need a 5-element set. We can take 1, 3, 4, 6, 8. That is a perfectly good subset of 8. Okay, and now let's define our map. So the map, I'll just denote like this. So here to get this product, I just have to pick a number that's at most 1, okay, a number that's at most 3, a number that's at most 4, a number that's at most 6. There. So this is an example of a set, of a pair, sorry, FS, that's in our set 9, 4. Okay, just so we see what that data is. Now let's go back to our proof. What I'm going to try to do is I want to construct a bijection. So we need a bijection from omega nk to snk, which is going to be the set of W in Sn such that the number of cycles is equal to k. Okay, so that's what I need to do. Given this data of S and F, I need to construct a permutation that has exactly k cycles. All right, so here's what my construction is going to be. I'm going to start by constructing a different set, a derived set. So given S, I'm going to define T as follows. So it's going to be the numbers up to n. Remember, S only goes up to n minus 1, so T is not going to be empty, such that n minus j is not an element of S. Okay, and let's do the example as we go. So what is T in this case? So what is T? T is going to be the set of numbers 1 to 9. So maybe we'll put those in. Such that n minus j is not in S. So here, what is 9 minus 1 is 8. 8 is in S, so this is out. Okay? 9 minus 2 is 7. That's in. It's not in S, so 2 is in. 9 minus 3 is 6. 9 minus 4 is 5. 9 minus 5 is 4. 9 minus 6 is 3. 9 minus 7 is 2. 9 minus 8 is 1. And 9 minus 9 is 0. Remember that this last guy is always going to be an element of T. So my set T, just to write it back in a sensible way, is 2, 4, 7, 9, which of course is going to be size K, not n minus K. This has size K. One thing I'm going to consider is n minus T. The complement of T is going to be 1, 3, 5, 6, 8. This is not S, right? Has size n minus k, but it has the same size as S, and that's going to be important. So with those guys in mind, let's go back to our proof. So we've got this guy T, and then we're going to write n minus T in descending order. And again, this is going to be the same size as S. This is an example of one of these proofs that I'm just explaining the proof to you, and I'm not showing you how we got there. Okay, so now I have to create a permutation. So in standard notation, because cycles are important, so I need to use standard notation for cycles. So standard notation for cycles is that I'm going to have gamma 1 up to gamma k, where the first letter of the gammas are the largest in each cycle. So the first letter in gamma I is the max of gamma I, and we have the max of gamma 1 is less than the max of gamma 2, and so on. So that's standard notation, okay? What I'm going to do is I'm going to tell you, okay, I need something of size k to make the cycles. I need k cycles, and here is some data that has size k. So I have no idea how to make that go away. Oh, okay, apparently I do. So we're going to make T has the beginnings of all the cycles. So let me go to our example, and we're going to start making our cycles. So we're going to have a cycle that begins with 2, a cycle that begins with 4, a cycle that begins with 7, and a cycle that begins with 9. And they're going to be written in this order, okay, for standard notation. And now what I have to do is figure out how to put all of these numbers in n minus t into this cycle. And so maybe before I write it down, I'll just show you what we're going to do. We've used the set S. We've heavily used the set S. So now what we're going to do is we're going to use that map T. So that map F. We need to use this map F, okay? And that was the point of writing these guys backward, So what I'm going to do is, remember to write F, I'm going to write 1, 2, 1, 3, 6. This is the image of F, so if you want, we can write it in two-line notation. But this is the part I care about for F. And now I'm going to write n minus t, and I'm going to write it in reverse descending order. So n minus t was a set 8, 6, 5, 3, 1. Okay, and now what I'm going to do for every number here in n minus t, so for each bi, I guess I will write this down. So bi has exactly f of ai larger letters before it. Okay, that's the algorithm. So what does that mean? That means, let's start with the 8. 8 has one letter bigger than 8 that comes before it. So the 8 has to go over here, right? That's the only way. The 9's the only thing bigger, so the 8 has to be over here. Okay, that takes care of the 8. Where does the 6 go? So the 6, according to this map, has two things that are bigger than it that come before it, okay? The 7, 8, and 9 are already placed. So I need two of those, exactly two of those, to come before the 6. So that means the 6 has to go here. Right, the 8's already placed in the cycle. We're keeping the standard notation, so now I place the 6. And now let's look at the 5. The 5 has one thing bigger than it that comes before it. So where does the 5 have to go? The 5 has to go here, into this block. Because remember, we can't touch the heads of the blocks. Where does the 3 go? The 3 has three things bigger than it that come before it. So just count them off. 1, 2, 3 things bigger than the 3, so I'll plunk the 3 right there. 3 is now placed. The 1 has 6 things that come before it that are bigger. 1, 2, 3, 4, 5, 6. The 1 gets squeezed right in here. So my permutation W, if I write it in a more sensible way, is 2, 4, 7, 5, 3, 9, 1, 6, 8. And that is it. So that is the proof. That is the combinatorial proof. We have combinatorially interpreted this generating function over here. We have a combinatorial set for which it's now the generating function, and we've made it equivalent over here. And this, again, is not something that you should necessarily come up with if left on your own. It's a very subtle construction. I've not proved that the construction is well defined, and I have not proved that the construction is injective. So, or surjective. So there's a lot left to the reader, but I'll leave that up to you. Hopefully this example at least explains the type of the construction and the flavor that it has.